Hey, welcome back to Fat Physics. This is example 2 in 6.1 part 1, talking about horizontal circles. Not your vertical ones, otherwise more forces will be involved. So, example 2, let's go. We have a car is traveling at 14 meters per second around an unbanked, which is just a flat ground, curved road that has a radius of 96 meters. So in a bird's eye view, it kind of looks like this. So let me use black instead. Okay, so this is the circle, the car. If I can draw a nice picture of the car right here. Okay, it's going around the circle, in which the radius here is 96 meters. The question is, what is the centripetal acceleration? And B, what is the minimum coefficient of friction between the road and the car's tires? Ooh, B is probably trickier. So let me first do A and explain B. A is pretty straightforward because we know the centripetal acceleration can be calculated by the tangential speed squared divided by the radius. Now, since the car is going at 14 meters per second around the circle, that is the car's tangential speed. So that's 14 meters per second, all of this squared, divided by the radius, which is 96 meters. Putting that into the calculator, we get 2.04166. And that's going to round up to about 2.0 meters per second squared, technically towards the center of the circle. But we all know that, so I'm just going to box that there. Question B is probably where we're going to have a bit of trouble. So the key in question B is to draw a free body diagram. In fact, I'm going to draw a free body diagram of this car from the behind view. So imagine we're looking at the car from behind. So let's see if we can do that. Okay, those are the tires, and the car is traveling along the road, but this road is curved, and which means that the centripetal acceleration of this car must be going towards the center of the circle. So let's draw a free body diagram acting on this car. First of all, we know there is gravity. There is the normal force acting on this car due to the ground, and there's one last force. This force has to be directed towards the center of the circle, otherwise there will be no F net to provide that centripetal acceleration. So there must be some other force directed to the center of the circle. We don't know what force this one is, but we have to think a little bit about it. Imagine this whole road the car is traveling is icy. If it's icy, what do you think this car is going to do? You're right, this car is probably going to go flying off everywhere and crashing to the side and hitting some pedestrian. Yes, so if the road was icy, the car would not be able to stay moving around in the circle. So then what force must be keeping this car going around in a circle that would be available if the road was not icy? If you're thinking about friction force, then you are correct. The friction force between the tires and the ground is allowing the car to stay in the center of the circle. Otherwise, it will start to skid off to the side if the road was too icy. Which is also why you might notice that some of you who drive, if you're going too fast around a curved bend, you might hear a little bit of or a skid with your tires in the ground, or you kind of imagine a heavy truck trying to turn a very sharp bend or whatnot, or just something trying to go very fast around a curved bend and potentially losing it, if you know what I mean. So this force directing towards the center of the circle is the friction force. And you're thinking, wait a minute, I thought friction force was acting against the direction of the car's motion. And yes, there is probably some friction. So if I drew the car from the side view, there's probably some friction directed that way as well. But in order for this car to maintain moving around in a circle, there's also an extra bit of force acting you can think of it acting horizontally against the tires, so allowing the car to stay in the center of the circle. Because think about this car. It wants to move away from the center of the circle due to its tangential speed, so that the friction force must act opposite to that tendency, which is directed towards the center of the circle. So that is why there is that force directed to the middle, providing the centripetal acceleration, is the friction force. So if we write the F net equation, then we're going to get F net towards the center of the circle is going to be equal to our friction force, and that is mass times acceleration, in which acceleration is the centripetal acceleration. We also know that the force of friction is mu times Fn, and this is where we get to use Fn from our diagram. We also know Fn is equal to Fg in this case, since there is no other vertical forces acting on the car, and there is no vertical acceleration. Okay, so in this case, we got, this is mu mg of the car, okay? So then we will then substitute force of friction over here. We're going to get mu mg times mass of the car times the centripetal acceleration, and you might notice something that could potentially cancel out in this equation. That would be the mass. You're correct. Hey, I didn't even give you the mass of the car, so good thing it did cancel out. And which reminds me that if anytime you think you're not given a value in the question that you think you'll need, that means you probably don't need it, because it probably will cancel out somewhere. In this case, it did, which means to get our minimum coefficient of friction, we're going to isolate this by dividing both sides by the gravity, which we are going to get mu is equal to centripetal acceleration divided by gravity, 9.81 meters per second squared. And centripetal acceleration we found earlier, which is 2.0416 repeated, and I'm going to divide that by 9.81, giving 0.208. 0.208 is going to round up to 0.21. No units for the coefficient of friction, so we leave it as 0.21. Woohoo! This is a very classic example of horizontal circles. Make sure you fully understand this problem, because it may come back in any shape or form. Alright, so good work, and we got one more example to go. Example 3. Thank you for watching. Fan Mama Physics signing out.